Good morning and welcome once again to the Applied Econometrics course. And today we will be discussing an advanced econometric model in the class of panel data, which is called dynamic panel data model, right? So, this is dynamic panel data model. Dynamic panel data model. Now, before we start discussing about dynamic panel data model in detail, let us try to understand what exactly we mean by dynamic panel data. Don't you think that panel data itself is dynamic in nature, because we are taking several years data and that itself gives a sense in our mind that panel data is dynamic while the cross section is static in nature. But that notion is actually not true, even though we take several years data while modeling a panel, constructing a panel, the panel data itself is not dynamic in nature. So, to start with, let us talk about the simple static and fixed effect panel data model what we have discussed earlier. So, this is YIT equals to, let us say, beta xit plus uit, a simple panel data model where we assume that this, let us say, this is equation 1 and we assume uit equals to ai plus vit. Now, you all know by this time what is ai, right? Ai basically is the individual specific time constant unobserved effect, right? And vit is the standard idiosyncratic error, and we assume that both ai here I running from I equals to 1 to n and t runs from 1 to capital T. And what we assume that ai follows I d with 0 mean and sigma square a variance, and similarly vit also follows I d with 0 mean sigma square v. What does it mean? That both ai and vit they follow an independent and identically, both of them are independently and identically distributed. That means there is no correlation between ai and vit, and ai and vit they are not serially related as well. Now, the question is, I have written a simple panel data model with equation 1, and the question is why it is not a dynamic one. Like the way we started our discussion, why not every panel data is dynamic in nature? Look at here, YIT, that means tth period y depends on the value of the x on the same period. If any changes happen to x, then y will also change and adjust itself in the same time period t. That means the changes in x will definitely result in a change in y, but the change is instantaneous in nature. That is why this model, the model 1, the equation 1, which indicates the panel data model, the simple fixed effect panel data model, what we are talking about is not dynamic in nature, because there is no dynamism, there is no persistence over a period of time. Any changes in x will result in instantaneous changes in y. That means this model is called instantaneous or instantaneous adjustment, and that is why this framework is called static panel data model. So, whenever you see this type of model, they are called static panel data model, because the adjustment happens in the same period. That means the adjustment happens instantaneously, right. So, that is why this model is called static panel data model, static panel. Why this is static panel? Because the adjustment is instantaneous. Instantaneous adjustment. Right? So, when we need to construct a dynamic panel data model, that means we need to introduce dynamism in the system. And how do you introduce dynamism in the system? Let us see. So, let us assume another class of model yit equals to beta 1 yi t minus 1 plus beta 2 xit plus ai plus vit. Now, what is the difference between model 1 and model 3? In model 3, we have introduced a lag dependent variable, and by introducing lag dependent variable, we are actually introducing dynamism in the system. So, that means if anything happens to yit minus 1, that will carry forward in the next period. So, that means yit depends its previous value, okay, its previous values. So, by including a lag dependent variable, we are actually introducing dynamism in the system. You can easily understand the difference between 1 and model 3. This is called a dynamic panel data model. So, this is a dynamic panel data model. Right. So, by introducing lag dependent variable, we are making the model dynamic. So, this model is basically not an example of an instantaneous adjustment, rather this is called partial adjustment model. So, yi cannot adjust itself in the same period, rather it also depends on its previous value. That is why this model becomes a partial adjustment model or dynamic panel data model. So, this is called partial adjustment, contrasting to the previous one, which was instantaneous adjustment. So, this is partial adjustment. Okay. Now, there is another class of model. Let us take this one, yit equals to beta 1 xi t minus 1 plus beta 2 xit plus ai plus vit. Let us say this is equation 4. So, instead of introducing lagged value of the dependent variable, now I have introduced lagged value of the independent one. Now, by introducing lagged value of the independent variable, do you think I have introduced dynamism in the system? Can you think of? Actually, the answer is no, because whatever happens to x, that means in the previous period's xi value, yit will adjust in the same period. So, just that instead of xit, or you can remove this xit also from the model, and you can simply say that this is basically yit equals to beta 1 xit minus 1 plus ai plus vit. So, instead of yit depending on xit, it just depends on the previous value of xit, but that does not mean that we have introduced dynamism in the system. So, this is not a dynamic panel data model. So, model will become dynamic only when we introduce lagged value of the dependent one. That is something which we have to clearly keep in our mind. So, this is not a dynamic panel data. This is not a dynamic panel data. Right. So, this model, dynamic panel data model given by equation 1 and 2, actually it introduces couple of problems regarding the as far as estimation is concerned, and let us try to understand what are the problems of applying ordinary least square method in estimating this type of model given by dynamic panel data. That means the moment you introduce lag dependent variable, it calls for certain problems that makes OLS to be inapplicable, right. Let us try to understand. So, I will write the dynamic panel data model once again. So, this is yi t equals to what was the equation what we have written earlier, yit equals to beta 1 yit minus 1, good, okay. So, beta 1 yi t minus 1 plus beta 2 xi t plus ai plus vit. This is our dynamic panel data model. Now, first of all, the question is why OLS is not applicable here. Okay. So, you can easily understand here yit is basically a function of ai. There is no t subscript here. So, that means I can say that even yi t minus 1 is also a function of ai. Simple logic. If yit depends on ai and see there is no t subscript at ai, so that means since yit depends on the unobserved individual specific and time constant, since this factor is time constant, it remains unchanged. If yit is a function of ai, yit minus 1 is also a function of ai. So, that means the covariance or correlation between yit minus 1 and ai is actually not equals to 0. And if you can recall, one of our 10 assumptions of classical linear regression model was that none of the regressor should be correlated with the error term. Okay. So, that means these two actually, this is nothing but uit, right. If I combine UIT actually one way error component model, that is why we assume this UIT equals to AI plus VIT. Just one second, I will mention it that here the moment I introduce UIT in this way, that means it basically indicates UIT is one way error component model, one way error component model. Why this is one way error component model? Because I have introduced only individual specific time constant effect. I have not introduced anything uh, 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 which accounts for the time effect. That means I have not assumed that even the times are also different among each other. So, a two-way error component means UIT would be AI plus some mu t, which does not change across individual, but changes only over a period of time. That factor is not there. So, since I have introduced only AI, this is called one way error component model. So, as you all know, there are two types of panel data model, one way and two way error component model. For simplicity's sake, for the time being, we are just assuming that this model is one way error component model, that is all. Now, here since this is correlated with AI, so that means I can say that covariance between YIT and this is basically UIT is not equals to 0. So, that means your one of your explanatory variable now become endogenous, right, that is the idea. So, that means one of the explanatory variables, become, so this indicates becomes endogenous, and that basically indicates OLS is not applicable. Okay. This is one problem. So, introduction of the lag dependent variable creates this problem, that one of my explanatory variable becomes correlated with the error term, right. Secondly, what happens here? Introduction of the lag dependent variable creates autocorrelation in the model. What happens? What I am saying that introduction of what I am saying, this is the point, that introduction of YIT minus 1 creates autocorrelation in the model. Okay, autocorrelation in the model. So, you might be thinking, how come YIT minus 1 is actually creating autocorrelation? And that is something we can easily understand. Here what I am saying that YIT minus 1 is basically a function of AI, right. So, how introduction of lag dependent variable creates autocorrelation in the model, that we are basically trying to understand. So, what is happening here? Here what is happening basically, what we are saying that YIT is actually a function of AI. So, YIT is a function of AI. YIT is related with AI, and YIT minus 1 is also a function of AI, right? Okay. Or we can say that this is not AI, this is basically YIT is related to VIT, and YIT minus 1 similarly would be related to VIT minus 1, right. The way YIT is related to VIT, if I write the same equation for YIT minus 1, obviously that would be related to VIT minus 1, okay, VIT minus 1. And since YIT is basically is related to this, YIT is a function of YIT minus 1. So, that means I can say that then VIT is actually a function of VIT minus 1. So, that means since YIT is related with YIT minus 1 and YIT minus 1 is related to VIT minus 1, YIT is also related to VIT. So, that means this is a correlation between VIT and VIT minus 1. Very simple to understand. So, I will explain once again. In this equation, what I can see that YIT is related to VIT, simple, because VIT is the error component in YIT's equation. YIT is also related to YIT minus 1 because YIT minus 1 is one of the explanatory variable. Since YIT minus 1 is again related to VIT minus 1, so that means what is happening? YIT is basically related to both YIT minus 1 and also indirectly with VIT minus 1, right. That is the reason VIT is again getting correlated with VIT minus 1. This is the logic. Okay. So, VIT is getting correlated with VIT minus 1 through this YIT minus 1, because YIT minus 1 is correlated with VIT minus 1 and YIT minus 1 is also correlated with YT. That is why the moment we introduce lag dependent variable in the model, it will lead to autocorrelation. And as we all know that if we have autocorrelation in the model, then we cannot apply OLS to estimate the parameters, because that will lead to inconsistent and biased estimates, right. So, introduction of YIT minus 1 creates autocorrelation in the model, and that implies again OLS is not applicable. Okay, OLS is basically not applicable, right. So, this is one type of persistence. So, that means the moment we introduce YIT minus 1, that will lead to autocorrelation, that is why OLS is not applicable. Previously, if you see what we have discussed, that if you come here, what we have discussed previously, that since YIT is a function of AI, YIT minus 1 will also become a function of AI, right. So, that means these two are two types of persistence over a period of time in a dynamic panel data model. First one is the autocorrelation created by the lag dependent variable. Second one is this, AI is also getting carry forward over a period of time, because AI component is there in the composite error structure. So, at any point of time, your error component will always be capturing AI, right. So, there are two types of persistence. That is why again and again we are discussing that OLS is not applicable. So, then naturally one question comes to our mind, why not removing this AI component, so that at least we will get rid of one type of persistence, like the way we were doing in our previous discussions in the context of fixed effect and fast differencing of the panel data model. Okay. So, since there is a problem with this individual specific time constant effect, which is creating one sort of persistence in the model, we are trying to eliminate this unobserved effect, individual specific time constant unobserved effect, by fixed effect transformation, and let us see what will happen. So, at least up to this stage what we have explained, that there are two types of persistence that is coming due to introduction of YIT minus 1. One is, this is number 1 and this is 2, right. So, what I will write the dynamic panel data model, creates two sources of persistence over time given by 1 and 2. Okay. One is explaining how the AI is getting carry forward over a period of time, because AI component will be there in the error term. What is your composite error term? Composite error term is UIT. So, similarly, since AI does not have any T subscript, AIT minus 1, AIT minus 2, AIT plus 1, AIT plus 2, in each period you will have AI. So, that creates type 1 persistence over a period of time, and type 2 is autocorrelation, right. And this autocorrelation is happening even though we have earlier assumed that this VIT is actually IIT. They are independently and identically distributed. Okay. And another type of problem of this type of model is that one of your explanatory variable is actually getting correlated with your error term. Okay. So, if we can remove AI from the model, then we can get rid of this endogeneity problem. At the same time, we will get rid of one type of persistence at least from the model. Okay. One type of persistence, that AI getting carry forward over a period of time. So, now we will see whether we can estimate this dynamic panel data model by simply a fixed effect transformation, which we have learned earlier.